Hey there, back again. Problem 5, and it looks like we're going to use a little L'Hopital. Going to be doing some derivatives. I do not have to show the requirements for L'Hopital's rule, so I don't have to take the limit of arc sine of 1 over root x plus 1 and show it equals 0, even though I know it will equal 0. And same thing for 1 over root x. I don't have to show that. I just have to execute L'Hopital's rule. So what L'Hopital's rule says is if you get the indeterminate form 0 over 0 or infinity over infinity, you're going to take the derivative of the top and the bottom and then reevaluate the new limit after you reduce. So what I'm going to do is I'm going to take the derivative of the numerator. So arc sine of 1 over the square root of x plus 1. That one's going to be pretty ugly. So let's see what we get. Gross. Derivative of arc sine is 1 over square root 1 minus denominator, the function inside the function. Wow, this one's ugly. Squared. Okay, so that's the derivative of arc sine of something. 1 over the square root of 1 minus the something squared times the derivative of the inside. And the derivative of 1 over square root of x plus 1 is going to be x plus 1 to the negative 3 halves over 2. Okay? And actually, I did goof that up too. It should be negative. So that right there is the derivative of arc sine of 1 over the square root of x plus 1. If you got questions with that, hammer that thing out on the side. I'll put it in a nicer form here, although this doesn't necessarily look that much better, but you'll see why I like it in this form in just a minute. Okay, so I got that over 2 square root 1 minus 1 over the square root of x plus 1 squared. Okay, now derivative of, ooh, this is much nicer. Derivative of 1 over root x will equal negative x to the negative 3 halves over 2. Okay. All right, so now what we're going to do to find the limit as x approaches infinity of this ugly thing, and yes, that is ugly, square root 1 minus 1 over square root x plus 1 squared over this slightly less ugly thing. We're going to get something a little bit nicer to work with. Okay, so first let's clean this up just a tad. Let's drop the 2's. Those 2's will disappear. The negative sign here, those will reduce. And then when I divide by x to the negative 3 halves, really I'm really multiplying by 1 over that. So let's take and rewrite this as the following: x plus 1 to the negative 3 halves over x to the negative 3 halves times this square root 1 minus 1 over root x plus 1 squared. Wow, that was terrible. Okay, hang with me here. That was pretty ugly. Okay, now as x goes to infinity, this thing will go to infinity, which means this thing will go to 1 over infinity, which is 0. So that's going to go to 0. Okay, now, if that thing's going to 0, then what I really have is x plus 1 to the negative 3 halves over x to the negative 3 halves times 1. All right, and that is going to, that's probably not the greatest notation. That's going to end up going to 1. Okay, you could use a number of different comparisons with that. However, that will end up going to 1 because the leading term will be x to the negative 3 halves. Okay, so using L'Hopital's rule, we've now found that that will go to 1. I'm guessing we're going to use that in a minute here. So let's go to part B. Ooh, this looks fun. Part B, 3 marks. Okay, 3 marks. Take that with a grain of salt. So when you see an intimidating figure like this, don't be frightened by it. Just consider the information and work through it. Okay, so it says, consider the infinite spiral of right-angled triangles as shown in the diagram below. Okay, the nth triangle in the spiral has central angle theta sub n, hypotenuse of a sub n, and opposite side of 1. So notice the commonality here. These are always 1s. Okay, that's going to stay the same. All right, the first right angle triangle is isosceles with 2 equal sides being of length 1. So let's find A1 and A2. I'm going to do my work up here. So in part 1, or part I, okay, A1 will equal root 2. Okay, so this is equal to root 2. So then A2 is going to be equal to the square root, I'm just using Pythagorean theorem, root 2 squared plus 1 squared. So A2 will be equal to root 3. Okay, so A sub n will be equal to, it looks like, if I take n and I add 1, I should get a sub n's length, which would be the square root of n plus 1. Okay, so show that, I'm guessing I'm done there, yep. Show that, part 2, theta sub n is arc sine of 1 over n plus square root of n plus 1. Okay, so let's set this up in general. So the sine of theta n is going to be the opposite side, which we all know, always know as 1 over the hypotenuse, which is a sub n. And we know that a sub n is always square root of n plus 1. Therefore, theta sub n is always equal to arc sine of 1 over square root of n plus 1. Cool. I would say this is probably, boy, I'd say that's probably 2 marks. And I'd say part 2 is probably 1 mark because it's just manipulation from there. All the information is already acquired. Okay, let's see what happens here in part C. It says for 6 marks, okay, a little bit more maybe to do here. Consider the series n equals 1 to infinity of the sum of all the angles. Use a suitable test and determine whether the series converges or diverges. Okay, so really what it's asking us for is to, I mean, you need to be able to identify that theta sub n we just found, and theta sub n was arc sine of 1 over the square root of n plus 1. Okay. Now, don't forget where you came from. In part A, we already did this. We did the limit as n goes to infinity of arc sine of 1 over the square root of n plus 1 over 1 over the square root of n. And we might have done it. Did we do it in terms of x? I can't remember now. I don't recall. Yeah, we did it in terms of x. So the only difference here between what we did there and what we're doing now is we're in terms of n. Okay, so at this point, we found that this equaled 1. This should be screaming limit comparison test to you. Okay, limit comparison test. Let's do a quick once over on that. The limit as n goes to infinity of an unknown sequence over a known sequence. So this is known, whether it's convergent or divergent, I don't know. I get to choose that. This is unknown. I don't know what this sequence is going to do. But if, let's say, for example, the known sequence is convergent and this limit comes out to be 0 or some finite number, then the two will act the same. So that means then this unknown one will be convergent. Likewise, in the opposite direction, if this is a known divergent and the limit comparison test comes out to be a countable number or uncountable, then this sequence and its infinite series will be divergent. Okay, so we found in part A that this limit equaled 1. Now I need to determine what I know here about this, because this is a known series, and this series, let's go n to the 1/2, right, is a known, pause the video if you need to think about it, but it is a known divergent p-series. That is a known divergent p-series. Now let me look at divergence, and I should have done this in blue, but whatever. If the limit comparison test comes out to be a finite number or infinity, this is a finite number, then the unknown series will act the same as this. Therefore, this series right here will be divergent by the limit comparison test. Okay, guys, that is, I believe, it for problem number 5. It's a good one. Please practice these. Look at the review documents that I have on all these convergence and divergence tests, and get used to practicing them, because they're not just going to show up plain as day. They might be hidden in a problem, kind of like this one. And of course, I mean, if you're paying attention, you're going to see that part A builds into parts B, which builds into part C. So you could overwork yourself easily if you don't refer back to what you already know. All right, that's all I got for today on this one. So let me know if there's any questions. See you in the next video.